In this chapter, we're going to learn about the quantum model of an atom. So far, what we did is what is called the nuclear model of an atom, where the nucleus was in the middle and electrons are outside. That model has not changed. That is still the same. But now we're going to get a little bit deeper into the atom and learn about where these electrons reside. Not so much about the nucleus, okay, but a lot more about the electrons in this chapter. So before we get into the electronic structure, let's talk a little bit about electromagnetic spectrum, okay? Because I need you to understand the concept of radiation, okay? And so the sun gives off radiation, and it's called cosmic radiation. When that radiation hits the Earth's atmosphere, it kind of splits into different radiations. It's kind of like when you keep a prism in front of light, then you can see a rainbow. It's that kind of a split. And when the split happens, then you get different wavelengths. And scientists have assigned different ranges of wavelength a particular name. Okay, and so the ranges are from 10 to the power of 13 to 10 to the negative 13, and this is wavelength given in nanometers, and so which means we have a really high range, okay, of wavelength. And in that case, the larger wavelength, 10 to the power of 13 nanometer. Now remember, nanometer is 10 to the negative 9. So which is right here, okay? 10 to the negative 9 is 1 meter. So this is the meter scale actually right here. So the radio waves are even larger than a meter. And then we get smaller and smaller over here as we go towards the gamma rays. So this is what we see in our atmosphere. We have a range from radio waves to micro to infrared to the visible, ultraviolet, X-rays, and gamma rays. Just to tell you a little bit about all these different radiations, the radio waves, really high wavelength, okay, large wavelength, 10 to the negative 11, 10 to the power of 11 and 13. And these were also one of the first regions to be used in the electromagnetic spectrum. Okay, and so radio waves are used, of course, for radios and TVs and all those. So you can listen to things, and that's radio waves. You get to a little bit higher or a shorter wavelength, and you get to the microwave, which of course we can't live without anymore. So that's where we cook food. So that's the range where you can heat food up. You get to a little bit shorter wavelength, and you get into what is called the infrared region. Infrared region is a little bit hotter now. Okay, radio waves don't feel anything at all. You can listen to as much radio as you want to. Hopefully it will not kill you. It will not kill you. Don't worry about it. But infrared, on the other hand, now it starts getting warmer, which means that you feel the radiation now. Okay, and infrared is not harmful, okay, but the fact is that you start feeling the heat. Okay, so some of the heat lamps, for example, those are infrared, and you may have heard of infrared goggles, which are used for nighttime vision, and those are all then based on heat. You can see the heat pattern of a body. Okay, that's how you see infrared. Then comes the visible radiation, and visible radiation is a very small portion of the electromagnetic spectrum, but boy, we are happy that it's there because it gives us all of these different colors. And again, the visible region is not harmful at all unless you're wearing really hot pink. No, just kidding. But otherwise, visible region is a very tiny region, and it, again, not harmful at all. Okay, and then when you get to the ultraviolet, then it starts getting a little bit dangerous. Okay, because now this is getting into a little bit higher region of energy, and so this is what is used in sun tanning, for example, or tanning beds. You know, if you go to tanning salons. So ultraviolet is actually not that good for us. One should protect your skin from ultraviolet radiation. But that's what comes after visible, and you feel the radiation like heat also, but sometimes you don't even know that you're being exposed to ultraviolet. So you have to just be careful. Okay, and here in Florida, we do experience the ultraviolet a lot because there's so much sun here. Then going on to the X-rays. Now with the X-rays, you're getting a little bit even more energetic, okay, because now the radiation can actually pass through your body and if it's going through your body, it obviously has high energy, okay? And if you've ever had an X-ray done, then you know that even the nurse doesn't want to stay with you, okay? She'll just leave you in the room and we'll see you shortly. And then we get to gamma rays. Gamma rays are one of the highest energy radiation, and not every location is supposed to have gamma radiation equipment. It's one of those monitored equipments, and so not everyone can have it. It's very high energy and very radioactive, and so one has to be really careful with the gamma radiation. The other thing I want you to look at from this slide before I go on is the units. Okay, so wavelength has a unit of nanometers over here, and see the wavelength is getting larger as you go to the right, okay, as we talked about before. Frequency is given in hertz, and we use hertz all the time these days, so it's not really a unique kind of a unit for you. Frequency is 1/nanometer, okay, but it's still called hertz, and actually it's not 1/nanometer. We'll talk about that. So but anyway, so frequency here is going in the opposite direction of the wavelength, okay? So as the wavelength is increasing, the frequency is decreasing, okay? And I want you to keep that in mind as we go on, because this is an important part in the electromagnetic spectrum. Regarding how much of the spectrum you should know, well, you have to know these different radiations and place them in order of increasing energy. I don't need you to remember the wavelength or the frequency, okay? But definitely the names of these radiations and how they are arranged. So let's talk about the wave nature now. As I said, that we will talk about this a little bit. So a wave is something like what you see here in the red color. Okay, it's going up and down, up and down. You see waves all the time at the beach, okay, when the wave comes to you. A wave has two properties. Actually, it has three properties. A wavelength, which is a crest to crest, or the distance from starting here, 0, and then one crest going down and one crest going up again to 0. Okay, so whole cycle, that is called a wavelength. It has an amplitude. An amplitude is the height of the wavelength. And then the third thing that it has is frequency. And frequency is the number of wavelengths that pass in 1 second. Okay, it's given right here. Frequency is the number of cycles, waves per second. So for example, if you look at wave number A, in this case, the wavelength is quite large, and so therefore you will have less number of wavelengths passing through in 1 second. As we go to B, the wavelength is getting smaller, so there is a higher frequency. And then by the time you come to C, the wavelength is so small, and so therefore the frequency is very high, which means that the relationship between wavelength and frequency is of an inverse nature. So you increase one and you decrease the other. So as I showed you on the slide, in the previous slide, where the wavelength was increasing and the frequency was decreasing, this is the reason why that happens. Okay, and so those are the three properties of a wavelength, okay, which is the wavelength, amplitude, and frequency. Okay, wavelength is given by this symbol. It's called lambda. Frequency is given by this symbol. It's called nu. Okay, Nu. So those are the two things that we really talk about a lot when we talk about electromagnetic nature and wave nature of anything. Regarding the amplitude, we don't really talk about it so much in chemistry, but just to give you an idea of how it is used is when you increase the volume on your radio, what happens is that you actually increase the amplitude. Okay, so nothing happens to the wave. Your music still sounds the same, or maybe it sounds more awesome, I don't know, but the frequency doesn't change. Okay, the tone of the music does not change, only how high you can hear it, how loud you can hear it is what changes, and that's the amplitude. Okay, so it doesn't change the wavelength and it does not change the frequency. So that's what amplitude is. Now the wave is related to each other. The frequency and wavelength are related to each other by this little equation, which is C is equal to lambda nu. C is the speed of light, which is the speed at which the radiation travels in space, and then of course lambda is the wavelength and nu is the frequency, which means that the speed of light is always constant, which is why you can multiply this these two things together, the wavelength and frequency, because as we also know, they are inversely related. So if they're inversely related, they have to be constant, and that constant is the speed of light. Here is a little problem on using that equation. So the wavelength of a laser pointer is reported to be 663 nanometers. What is the frequency of this light? Just a simple cross multiplication over here. So remember, C is equal to lambda nu. So if you're trying to figure out nu, all you have to do is divide C by lambda. Okay, and that's how you get the frequency. So really not very complicated calculation. A little bit about the nature of light. So when physicists started studying what light is and how it travels and things like that, a British scientist discovered that light has a wave property. Okay, and what that means is that it can be diffracted. Diffracted means that if you have light going in waves, and if it goes through a slit, then it will start going in circles, okay, like this. It comes out like this, and this is called diffraction. And you may have seen diffraction if you've ever thrown a pebble in or a stone in still water, okay, and that's when a wave will start forming like this in circles. It will never form in a straight line. Okay, it will always be a circle. It may seem a straight line if the circle is too large. Okay, but otherwise it will be what we call a diffraction pattern. So which means that we knew about light, that it is actually a wave property. Okay, within 100 years, a photoelectric effect was discovered by Hertz. And what photoelectric effect is that if you shine light on a piece of metal, then electrons will be ejected from that. What that really means as a discovery point is that light actually has energy. So initially, if you think about light as what it is around you right now, you don't see it, so you don't really know what its properties are, how it's traveling, what its energy is, and things like that. Okay, so all of these studies are actually trying to understand what this radiation is around us. So first we know that it's a wave, it travels like a wave. Okay, light travels like a wave. And then the second thing that is discovered is that it has energy also. So this is where the problem actually occurred then. After photoelectric effect was discovered, then it became a problem, because then if light travels like a wave, then how does it have energy in it? Okay, because to have energy, you have to have something in it. So for example, like heat has energy, an object has energy, but radiation is just radiation. It's not an object, okay? And so that's where the little bit of problem was with the nature of light. And this whole study was going on when there was a whole lot of discovery going on in many areas. So this is the end of the 19th century, and at the turn of the century, there were just so many things discovered, so many great scientists. And one of them was Max Planck. So then comes Max Planck, and he suggested his own theory, which is called the quantum theory, and which is actually the starting point for a whole new idea and a whole new way of thinking about light and waves. And what he said is that the radiation energy can be only emitted or absorbed in discrete quantities. Think about the photoelectric effect, okay, the fact that if radiation hits the metal surface, then electrons are ejected. But what he's saying is that if they're ejected and that radiation is hitting the metal surface, that radiation that is hitting is coming in discrete packets, okay, in small amounts. It's not a continuous radiation. That's what means by this discrete quantity. And those discrete quantities, that's called quantum. That's what he called it, quanta and quantum. And it's the plural and singular. And those are actually packets of energy, all right? And so it completely changed the way people think about energy, because we think that energy is continuous, and we don't even think that wave actually has energy for that matter. So it completely changed our way of thinking about waves and also about energy, okay? Because nobody thinks that energy comes in small packets. And the way he connected this whole thing with the wave is by this little equation, okay? E is equal to h nu, where E is energy, h is Planck's constant, and nu is frequency, okay, as we know it. So E and nu are on the same side, which means that they are directly related to each other, which means that if you increase the frequency, you also increase the energy of that particular radiation. And remember, if things are proportional, then they have to be, there has to be a constant in there. And the constant there is h, which is Planck's constant. So in any case, this is how one can calculate how much energy is in a particular frequency in a wave. So Max Planck was the first one to actually make that connection between waves and energy. So now when we look at the photoelectric effect, we can think of it a little bit differently also. By the way, Einstein also looked at this, Albert Einstein, as we all know, two-time Nobel Prize winner. Einstein also looked at photoelectric effect, and what he did and what he said is that the particles of lights are really photons. And he also suggested the same kind of thing. So it was kind of parallel in their discovery. And he calls them photons, which are packets of energy. And he related that energy also to frequency. And of course, he used Max Planck's equation for this. And Max Planck called it quanta and Einstein called it photons. Okay, that's the only difference, but otherwise they're both related in the same way. What Einstein also suggested is that there is something called threshold frequency, which means that you have to have a certain amount of energy in order to eject that particle in photoelectric effect. Okay, so for example, if you have red light that is hitting a metal, it may not eject any electrons. However, if you increase the frequency of that and go on to say blue radiation or say ultraviolet radiation, then the electrons can be ejected, okay, which means that there was a certain amount of energy that was required in order to eject those electrons. The other thing he also said is that the higher the frequency, then more electrons will be ejected, okay, and so of course this has been tested now. So higher frequency means higher energy, and that means more electrons will be ejected. So which means that there is a direct correlation of energy and frequency. Okay, the only reason you will have more electrons being ejected from something that has higher frequency is if it has more energy coming through. And again, remember the relationship between frequency and wavelength. Is that if one is low, the other one is high. Okay, so if you have a high frequency, that means it's a low wavelength, which means that there are more of the waves coming through, which means if there are more waves coming through, that means you have more photons coming through. And if you have more photons coming through, then you eject more electrons. Okay, so that's the relationship between frequency and photoelectric effect. So let's look at a problem over here, okay, which is trying to calculate how much energy there is in a photon with a wavelength of 700 nanometers. Now you might think, oh my goodness, I'm not given any other information. And that is because the other two pieces of information you need are constants, okay? And so you start with the wavelength over here, which is 700 nanometers, convert that into meters, use this equation that we used before where speed of light is equal to lambda nu, and calculate the frequency, okay, because for calculating how much energy there is in that particular photon, you will need to use Planck's constant, which requires frequency. So you calculate frequency from C is equal to lambda nu. Once you have that, you multiply that by Planck's constant and you get this energy, okay? And so energy here, if you look at the numbers, it's actually very small, 10 to the negative 19th joules. So it's a very small amount of energy, which is perfectly fine because 700 nanometers is actually the red color radiation, invisible light, okay? And so we are really happy that it's not very harmful, okay, to us. So in any case, that is how you calculate the amount of energy in a particular wavelength. So let's see how everything that we have studied so far helps us in our understanding of the atom. So we learned about wavelength, we learned about energy, frequency, Planck's constant, photons, and all of those wonderful things that link energy to a wave. So how does that affect us? Okay, and that was connected by Niels Bohr. He was a chemist studying the structure of atom. And one of the things that he did was to take an element and irradiate it with light. And once he did that or gave it energy, Once he did that, light was emitted, or energy was emitted from that element. And he studied that, and it seemed that all the energy that came out in discrete spaces, okay? Which means that the light came out at a very specific location. This is what he called the line spectrum. And once he changed the element, the line spectrum changed, which means that now the energy was coming out at a different location. And any number of elements that were studied gave a different line spectrum. But the commonality between all of them was the fact that energy was coming out in discrete locations, in very specific locations. It was not, as we would call it, continuous. Okay, a continuous would be when something merges into the other, like the electromagnetic spectrum. Okay, but this was what we call a line spectrum. So it turns out that each element has its own emission spectrum, its own line spectrum, and these are generally referred to now as the fingerprint of an element. So on the next slide, we have a few examples of what line spectra look like. So for the first few elements, hydrogen, helium, lithium, sodium, calcium, strontium. So some of these elements, and if you look at their spectra, and this is the line spectra, which is also called emission spectrum because you're looking at how light is being emitted. There are two kinds. You can have absorption and you can have emission. So this one is emission. So here light is being emitted in the blue region. Here it is getting to the red. But then look at helium. Helium has a very different line spectrum than hydrogen, and then lithium has a very different one from helium, and so on and so forth. So all the elements that we have, 119, 117 elements that we have on the periodic table, they all have very unique looking line spectrum. In your PowerPoints, you can go to this web page over here and check out the link. It's really quite interesting. It shows you all the line spectra of all the elements. So then a model was developed by which you can actually predict a line spectrum of any element. And the first element that was studied was hydrogen then. And Bohrs and Rydberg, two chemists slash physicists, they came up with an equation that can help them calculate the different spectral lines in hydrogen. And eventually you can calculate for any other element also. And with Bohr's equation, you can calculate how much energy is required, okay, to go from one location to another location, because it seemed that what was happening was that electrons were jumping around to another location, and when they came down to the original location, certain amount of energy was given off, which is what was giving the line spectrum, not a continuous spectrum. So which means that there was some sort of a transition going on in an atom. And so we call those ground states and excited states. Ground state is the lowest energy state of an atom, and excited state is when that n, the ground state, is more than 1. And so when the electrons jump from one location, one n, to another n, then a spectral line is formed, whether it is the absorption or emission. Okay, and absorption would be when energy is absorbed to go from a lower energy to a higher energy, and emission is when it comes back from that high energy state to a lower energy state. Now remember, in all of these things, electron is not being ejected. It's not being removed from an atom. It's only jumping around from one location to another. And what Bohr is trying to say is that that location is a very specific location. It's nowhere in the middle somewhere. It is actually one location to another location. The electron does not stop in the middle anywhere. And that's why you end up getting a line spectrum instead of a continuous spectrum. So we can use Bohr's equation to calculate the energy of these transitions. And so with all the different equations that we have, we can combine all of them and finally get this equation, okay, over here. So we have the Rydberg's equation, we have Bohr's equation, and of course we have the Planck's equation. Okay, how can we forget Planck? Because Planck is the one who links energy to frequency, all right? And so that's an important equation. So once all of these equations are combined, now you have this wonderful equation where h is Planck's constant, nu is the frequency, RH is the Rydberg constant, which is given over here in joules, and final and initial. These are the different levels at which the transition is taking place. So final and initial. These numbers are integers. They're not zero for sure. So there are 1, 2, 3, 4. they're not fractions, okay? And so these are whole numbers more than zero, not zero at all. So more than zero, it's 1, 2, 3, 4, 5, 6, whatever it could be. But anyhow, so this h nu here gives the energy that is required to take one electron from one location to another location. And so when you go from a lower location to a higher one, then energy will be absorbed. If an electron is going from a higher location to a lower location, higher n to a lower n, then the energy will be given off. Okay, and so in case when light is absorbed, then delta E, which is a change in the energy, will be positive because energy is being absorbed. And when light is emitted, then delta E, the energy change will be negative because now energy is being given out. Okay. And when the electron is ejected, then n final is infinity because now the electron does not even belong in the shell anymore, okay, or in the atom. So this shows us the line spectrum of hydrogen and the transitions that actually occur to give that spectrum. So here's the line spectrum, okay, where you see 4 lines coming out of very specific locations. And then here are the different transitions, okay. So we have n is equal to 1, which is the lowest energy. Then n is equal to 2, 3, 4, 5, and so on. One of the things I would like you to note before we go any further is that the distance between 1 and 2 is so much, okay? And then you go from 2 to 3, it gets smaller, and then smaller and smaller and so on, okay? So the distance between 1 and 2 is the greatest. So here is the Bohrs series, okay? This is what I want you to look at right now because the Bohrs series is in the visible region, and for hydrogen you see 4 line spectrum, okay, or 4 lines in the line spectrum. And so here are the 4 lines, okay, and this is what Bohrs was able to calculate and predict, okay, as to where these radiations would come. And that's theoretical chemistry in a way. Here is a problem which will show us how to do these calculations. So the problem is, what is the wavelength of light emitted when the electron in a hydrogen atom undergoes the transition from n is equal to 6 to n is equal to 3. So it's not from n1, okay, it's actually, you can calculate the energy and wavelengths from anywhere, okay, in the middle. So here are our numbers. For n initial, we are going from n6 to n3. So really we're going from a higher location to a lower location. As it is, we know that our energy should be negative. Rydberg constant, this is the equation that we're going to use then, where delta E is equal to the Rydberg's constant, remember, and then n final to n initial, okay? And then we will also use this equation, okay, to find out the wavelength, all right, because that's what we need, and wavelength is calculated from right here. So first of all, let's find the delta E, okay, which is the amount of energy that is given off or absorbed. And in this case, as we said, it should be given off because you're going from a higher location to a lower location. So this is how you would set it up. And you get this value and it's negative, and we are thankful for that because then we know that our answer is correct. If it was positive, then we know we've done something wrong. So going from a higher energy level to a lower energy level, energy should be given off. So this is the delta E that we just calculated, and now we have to go ahead and plug it in the Planck's equation, or this equation, sorry, for delta E, because we need to find out the wavelength, okay, of that light at this particular energy. So then we go ahead and do this, write this equation where we have lambda is equal to hc, h is Planck's constant, c is the speed of light, and delta E is what we just calculated, and that will give us the final answer. And this is the wavelength, 1.094 times 10 to the negative 6 meters is the wavelength of the light that is emitted. Okay, so that is how you solve these problems. Now the most important thing is for you to make sure that you have your initials and finals, okay, at the right spot. So again, the best way to check your answer, if it's correct or not, is see if you get a positive or a negative number. That is one of the quickest way to find out if you're on the right track. So here is a collection of all that we've talked about, okay, so far. where we have Planck, okay, who said that atoms will have certain energies, Einstein, who said that energy is quantized into photons, and then of course Bohr, and he was able to predict the values of energy that would be required for electron transitions from one location to another. So how do we use all the information that has been given to us so far, or that we have learned so far about wavelengths and light, photoelectric effect, photons, quanta, line spectrum, and the fact that Niels Bohr established the fact that electrons go from one location to another location, and when they do that, they either absorb or give energy in a particular amount or in a particular location. All right, and so how do we use that? So let's take a step back and go into light again. Okay, and we know that by now that light has both properties of a wave and particle. That was established by Max Planck, and the particles that he mentioned there are actually the quanta, okay, which Einstein called photons. But what about that matter is that it's so unique, okay? And so that was studied a little bit further by Louis de Broglie, a French physicist. And what he said is that particles, or any matter for that matter, will have wave properties, okay, which means that any matter will travel as a wave, okay, which means that it could be a table, a chair, TV, whatever, okay, it might be. Everything is traveling in waves, okay. Then why don't we see the waves? You don't see the waves so much because it is dependent on mass. So the higher the mass, the larger the wavelength, okay. And so very heavy objects are still traveling in waves, but you don't really get to see it because the wavelength is so large, okay, of that particular object. So, but in any case, this is an important discovery, because once he says that everything is traveling in waves, then Schrödinger took that up and he said, well, then electrons may also be traveling in waves then, okay, because electrons are found in certain locations as established by Niels Bohr. They're in a particular location, but in that particular location, electrons are still moving around in waves, okay? And so then came Heisenberg and said, well, okay, if they are traveling in waves, then how do you know where they are? Which means that you really cannot predict where they are, because their position and their momentum, which means the fact that they have a particular location and they're moving, how can you predict? Okay, it's almost like a car racing, okay, on a speedway. So if you have even 4 or 5 or even one car that is racing in a speedway, then you can either look at the speedway at the track, or you can look at the car. You can't look at both. And that's what Heisenberg is saying, is that you can't really track the location of an electron because it's in motion all the time, okay, and because it's moving, you can't tell, okay, where it is. And also the fact that electron is so small, and this movement is dependent on mass as established by de Broglie, then it's really very hard to predict, okay, where that location might be. So between the three scientists, Broglie, Schrödinger, and Heisenberg, we kind of understand that electrons also travel in waves. Electrons, of course, being so small, you can't really pinpoint the location of an electron. Okay, so that's what Heisenberg established. So then Schrödinger came up with another thing, which is called wave function. He said, well, okay, well, you can't tell exactly where the electron is, but you should be able to at least say that the electron is in this general area. And that's when he came up with the wave function. So this is just a little figure to remind you of what a wave looks like. And so this region here, where you have the down, the negative crest, and then there is a positive crest, and he assigned these locations psi, okay, and psi psi is a region, okay, given to a wave. It is nothing with absence or presence of anything. It's just a region. And then psi square gives us the probability of finding a particle, okay, in that region. So for example, when an electron has a particular wavelength, then you can find electron in this region and you can find an electron in this region. You cannot find the electron over here, and that point is called the node. Okay, we will talk more about the node later also, but that point is called the node where you have absolutely no probability of finding an electron. So with all of these different kind of studies, we now know that electrons travel in waves. You cannot pinpoint the location. All you can do is tell this might be a region where you can find an electron, okay, where there is a probability of finding an electron. That's what all of this is connected. That is how we know where these electrons exist and how they actually exist. In the next portion, we're going to delve deeper into how they exist in these locations also, okay? But for now, this is what we have. So from this section of the chapter, I would like you to know the electromagnetic spectrum, be able to tell me which region has higher energy, which one has lower energy or wavelength frequency, which means know the relationship between all the three, be able to do some calculations. I will give you the constants and the equations. You just have to do the calculation. Understand what quanta is, photoelectric effect is, emission spectrum. You don't have to memorize the emission spectrum of or a spectra of any of the elements. That's all right. That's not the point. The point is to be able to do some calculations using the ground state versus excited state, the Heisenberg equation. You should be able to do that. And of course, know the contribution of all the scientists who help to understand the structure of atom. Heisenberg, Niels Bohr, Schrödinger, de Broglie, okay, all of those. So this is what you need to know.